Hello everyone, my name is Hoàng Ngo and I'm going to present to you a work on massive uncoordinated access with random user activity. And this is a joint work with Alejandro Lancho, Giuseppe Durisi, and Alessandro Amat, and we are working at Chalmers University of Technology. To start, in multiple access, we are dealing with the problem of multi-user interference, and traditionally, we have been trying to avoid this interference by using graph-based communication and orthogonal access. So these are the solutions that have been implemented in wireless standards. But now we have some new challenges to this problem that are coming from the Internet of Things. So first of all, the number of users accessing the channel can be extremely large. These users are battery limited. Their activity is sporadic and time varying, and they transmit short packets. In order to deal with these challenges, a novel theoretical framework has been proposed by Polyanskiy in 2017. So now we recap the key definition in that paper. Here we consider a multiple access channel with Ka users, where Ka is assumed to be fixed and known. The channel is assumed to be memoryless and permutation invariant. So any permutation of the Ka inputs does not change the conditional probability. Well, the random access code proposed in this paper has three new elements. First of all the users use the same codebook to select the code words. Second, the decoder, based on the observation at the channel output, will produce a list of messages without specifying which message was transmitted by which user. Well, third, the error probability is defined per user. So there is an error if the transmitted message by a user is not included in the list of decoded messages, or if there is a collision between the transmitted messages. Well, in this framework, we are particularly interested in the Gaussian mark. So here, the channel output is the sum of the channel inputs and the Gaussian noise. And for this channel, we consider a power constraint. So the transmit power over a frame is upper bounded by NP for every user. We define the energy per bit, the AB over N naught, as the transmit power over a frame, normalized by the number of bits that are transmitted in a frame. So the main question here is to characterize the energy efficiency, or in other words, to find the lowest AB over N naught to guarantee that the error probability does not exceed a given threshold epsilon. Well, a key result in the paper of Polyanskiy is a random coding bound for this channel. And after that, there have been many schemes that are proposed to get closer and closer to this bound. So those are some nice results in Polyanskiy's framework. Well, here, we'd like to mention again an important assumption in that framework, which is that the number of active users, Ka, is fixed and known, so that the receiver is able to return exact Ka messages. And whenever we have a misdetection, we also admit a message that was not transmitted. So we commit a false alarm. So a misdetection implies a false alarm and vice versa. So these two types of error become indistinguishable. Well, in a practical IoT system, the number of active users is random and unknown a priori. So the receiver has to guess it. It has to guess how many messages it should output. But it can make a wrong guess. It can output too many or too few messages. So it can commit both misdetections and false alarms. And there is a trade-off between these two types of error. In order to account for this, in our work, we extend the random coding bound of Polyanskiy for this practical setting where Ka is random and unknown. We characterize a trade-off between misdetection and false alarm. We provide a more realistic benchmark for the energy efficiency of practical systems, practical schemes. Well, so let's get into the details. Here, for Ka random and unknown, the channel is characterized not only by the conditional probability, but also by a probability mass function of Ka, which is assumed to be known. We denote the list of distinct transmitted messages by W and the list of decoded messages by W hat. And we define the misdetection probability as the average probability that a message transmitted by a user is not included in the list of decoded messages. And the false alarm probability is defined as the average probability that a decoded message was not actually transmitted. So for this channel, we define a random access code for the codebook size M, block length N, and a pair of requirements for the misdetection and false alarm probabilities. And this code is a pair of possibly randomized encoder and decoder such that the misdetection probability is upper bounded by a given threshold epsilon MD, and the false alarm probability is upper bounded by a given threshold epsilon FA. So now we focus on the Gaussian mark, and we propose to use the following random coding scheme. First, for the encoder, we use the same Gaussian codebook as in the paper Polyanskiy. So we fix a transmit power P prime, which is smaller than the constraint P. We generate M code words as Gaussian vectors with zero mean and power P prime. So to convey a message WI, user I will transmit the corresponding code word if the code word does not violate the bound constraint. Otherwise, it transmits 0. Now the main difference is in the decoder. It has 2 steps. In the first step, we estimate Ka by Ka prime, which is a number between the lower limit KL to an upper limit KU that minimize a chosen metric. So here KU and KL are chosen such that the probability that Ka is between KL and KU is high. And we use these numbers to avoid infinite sum. So, for example, if we use maximum likelihood estimation of Ka, then the metric is given by the minus log likelihood of the output given the number of active users. If we use energy-based estimation, then the metric is given by the absolute difference between the received signal power and the average received signal power if K users are active. So having estimated Ka, we estimate the list of transmitted messages. We use a similar decoding metric as in the paper of Polyanskiy. So we look for the list of code words that minimize the Euclidean distance between the sum of the code words and the received signal. And the main difference is that our decoder doesn't know the number of transmitted messages. So it has to guess this number. And we let it to search for the best list size within an interval around the estimate of Ka. So here the interval is effectively from Ka prime minus R to Ka prime plus R. And R is referred to as the decoding radius. Well, with that random coding scheme, we are going to derive a random coding bound using the following technique. So here we write the misdetection probability as the average ratio between the number of misdetected messages, W0, and the number of distinct transmitted messages, W. And the false alarm probability is the average ratio between the number of false alarm messages, W0 prime, and the number of decoded messages, W hat. So in the first step, we change the measure such that all the users are transmitting different code words, and the number of active users, Ka, is from KL to KU. And also a selected code word is transmitted even if it violates the power constraint. In the step 2, we are going to count the number of misdetections and false alarms. So here we illustrated using a Venn diagram. The circle on the left represents the list of transmitted messages. The circle on the right represents the list of decoded messages. And the intersection is the list of the correctly decoded messages. So here we have the list of misdetections, W0, and the list of false alarms, W0 prime. Now, for the misdetections, we can actually partition W0 into two parts. For the first part, notice that the decoder can output at most Ka prime bar messages. So if this number is smaller than Ka, then we have a number of misdetections that cannot be avoided. And we denote these misdetections as initial misdetections. We assume that on top of that, we have T additional misdetections in the decoding process. So the total number of misdetections is T plus this number. Now for the false alarm, similarly, we can divide the list into two parts. The first part contains the initial false alarms that cannot be avoided. And we assume that on top of that, we have T prime additional false alarms. So the total number of false alarms is T prime plus this number. Now we are ready to expand the expectations in the misdetection and false alarm probabilities. Well, the misdetection probability is computed as the sum of all the realizations of this ratio multiplied by the corresponding probability over all the possible values of Ka, Ka prime, and T. And here B0 is an additional term that comes from the change of measure in the first step. Well, similarly, for the false alarm probability, we compute it as the sum of all the realizations of this ratio, all multiplied by the corresponding probability over all the possible values of Ka, Ka prime, and T prime. So now the remaining step is to bound these probabilities in red. Well, we bound the first probability by the probability that we have Ka active users multiplied by the minimum of probability that we have T additional misdetections, and the probability that having Ka active users, the estimation of Ka gives Ka prime. And similar for the second probability. Now the probability that we have Ka active users is given by the PMF of Ka. We are going to bound the terms inside the mean. So the first term inside the mean, which is the probability that we have T additional misdetections and T prime additional false alarms, is can be upper bounded by using a Gallagher type arrow exponent analysis. These terms can also be bounded using a property of the information density. So these two approaches follow similar lines as in the paper of Polyanskiy. Now for the remaining term, which is the property that having Ka active users, we estimate it by Ka prime. This is given by the property that Ka prime is a minimizer of the metric that we use to estimate Ka. And this probability is upper bounded by the mean of the probability that the metric at Ka prime is smaller than the metric at K, and the minimization is over all the K different from Ka prime. So with that technique, we can derive a random coding bound, and now we are going to show how the bound looks like. Here we consider a system with Ka following a Poisson distribution with a mean from 0 to 300. We assume that each user transmits 128 bits over 38,400 real channel uses. And we plot the required energy per bit such that we achieve 0.1 for both misdetection and false alarm probabilities. So first of all, the blue curve is the bound of Polyanskiy average over the distribution of Ka. So this corresponds to the setting where Ka is random but known. Now, our bound for Ka random and unknown would be above this. But how much above? Well, it turns out that our bound is only 0.5 to 0.7 dB above this bound of Polyanskiy. So it seems to suggest that the loss because of the unknown number of active users is not much. Our bound can be used to analyze performance of a slotted aloha with multi-bucket reception scheme. So in slotted aloha, the number of users transmitting in a slot is unknown. So we can apply our bound to in a slot by slot manner to account for both misdetection and false alarm in slotted aloha. So here, the dashed curve represents the case when we know the number of active users per slot, and the solid curve represents the case when we don't know this number. We also show the performance of some state-of-the-art schemes that perform well when Ka is known. Here, in order to adapt these schemes, we first estimate Ka, and then we use this estimate as a true value in the decoding process. And here we plot the required EB over naught of the sparse scheme proposed by Fengler and others in 2019. We also plot the performance of an enhancement of Spark proposed by Amat and others in 2020. And it can be seen that these schemes are performing quite well in when the number of active users is high, and the gap to our bound is about 3 to 4 dBs. So here's the message is that our bound can be used to benchmark the energy efficiency of practical schemes. Well, another aspect that we would like to present is how to choose the decoding radius. So recall that the decoding radius specifies how much the receiver deviates from the estimate of Ka in order to search for the best lead size. So here we consider the same setting as before. We fixed the number of active users, the average number of active users to be 50, and we plotted the misdetection and false alarm probabilities over the energy per bit for different values of decoding radius. So if the decoding radius is 0, then the misdetection and false alarms are almost on top of each other, and they drop quite quickly in the beginning, and then they saturate to an error floor in the high energy per bit regime. Now, if we increase the decoding radius to 1, then we get that the performance is worse when the EB over naught is low, and we only have improvement if the EB over naught is high enough. Similarly, if we continue to increase the decoding radius, then we get a worse performance in the low EB over naught regime and a better performance when the EB over naught is higher. The reason for this is the effect that we call the noise overfitting. So basically in the low energy per bit regime, the power of the noise dominates the power of the code words combined. So our decoder will end up trying to fit the noise rather than fitting the transmitted code words. And here, increasing the decoding radius make it worse because it enlarges the search space, and it increases the chance that the decoder will find a list of code words that match very well with the noise, but not so well with the list of transmitted code words. Okay, so this is my last slide. That's some takeaway messages. So in our work, we have extended Polyanskiy's framework for massive uncoordinated access to a practical setting where the number of active users is random and unknown. We derive a random coding bound for the Gaussian mark. We characterize a trade-off between misdetection and false alarm, and we provide more realistic benchmark for the energy efficiency of practical schemes. Thank you for your attention.